started. A relation is a connection between two quantities, right? It's a relationship between two things, or a comparison between two things. Cell phones away, please. Okay, so a relation can be represented graphically by a set of what? Ordered pairs. Coordinates are ordered pairs. Ordered pairs. The first component of a set of ordered pair is the x-coordinate, also known as the input. Values of the input are also values of the independent. Good. Independent variable. The second component would be the y, also known as the output. Values of the output are values of the dependent variable. Good. So today we're going to learn about x and y intercepts. So what do you think an x and a y intercept is? Like, what's an x-intercept? If you had to break down the word x-intercept. So first of all, x, we know what x is, right? X is horizontal. But intercept, yeah? So where the line crosses through the x-axis. So if we have a line or a curve or anything, this would be our x-intercept. Where the line crosses the x-axis. And then again, the y-intercept logically is where the line crosses the y-axis. Would be your y-intercept. Okay. So we're going to learn how to algebraically determine your x and y intercepts today, as well as graphically. Well, graphically is easy because we can look at it, right? So in this graph right here, graph 1, where does it cross the x-axis? At what coordinate? -3, 0. -3, 0. Good. Graph 2, where does it cross the x-axis? There's two coordinates. The first, -2 and 0, and then +3 and 0. And then the circle, -4 and 0, and +4 and 0. What do all of these have in common?
0.
What 0? Y. So at the x-intercept, or the x-intercept, I guess you could just say, the x-intercept is when y is equal to 0. Good. Super important. Okay. So let's look at our y-intercepts now. So graph 1, what's the y-intercept? What would be that coordinate? X is 0, 5. X is 0, y is 5. Okay, what about on this guy, the graph 2? 0, 6. And graph 3, 0. X is 0, y is 4, and 0 and -4. And so obviously, what do these have in common? The x is 0. So the y-intercept occurs when x is equal to 0. Okay, so that's going to be our guiding principle. Algebraically, if we know that the y-intercept is when x is 0 and I have an equation, I can just set x to 0 and solve for the y. Or vice versa. If I know the equation and I wanted to y equals 2x plus 3. Okay? I wanted to know, where is the y-intercept? Well, the y-intercept occurs when x is 0. So could I not just set x to 0 and find what y is? Yeah, it would be 2 times 0 plus 3, 3. 2 times 0, 0 plus 3 is 3. And so the y-intercept here, when x is 0, y is 3. That would be my y-intercept. The same idea for the x-intercept. That's what we're going to be doing today. Okay, is using this whole concept that it's where we're crossing the x-axis. Well, when we cross the x-axis, y is 0 every time. Okay? All right. So I just explained all of that. That's a lot of words, right? So essentially, if you had a highlighter or a pen to underline, where's my highlighter? Okay, the x-intercept seems so dark. I wish it was brighter. Is when the y-coordinate is 0. Right? It crosses. It's where we cross the x-axis. It's where the y-coordinate is 0. The y-intercept is when the x-coordinate is 0. Okay. So all of this is what we just talked about. That's the key stuff. If we want the x-intercept, we set y to 0. If we want the y-intercept, we set x to 0. Solve for the other. Okay? So here's an equation. I want the x-intercept. Who's 0? Y. So set y equal to 0. So we're going to take this equation of 3y equals 5x plus 15. Let me zoom in. Is that big enough or larger? Is that okay? Or do you want it larger? Those at the back. Good? Okay, so set y to 0. We're going to solve for x. 3 times, we're going to replace y with 0 equals 5x plus 15. What is 3 times 0? 0. Good. Okay, we want to isolate x. Remember when we isolate a variable, we're going to do opposite of that best. Good. Subtract 15. So subtract the 15, so you have negative 0 minus 15 is negative 15 equals 5x, and then divide by 5. So x is negative 3. So the x-intercept is equal to negative 3. Okay, y-intercept. We want the y-intercept. We're going to set who to 0? X to 0. Okay. So we have the same equation that we start with the original equation, but this time I'm going to take my x value and replace it with 0. When we replace a variable, it's always good to replace it inside brackets. It's always a lot safer. Replace it with brackets. Right, 5 times 0, 0 plus 15, 15. And then now we can just divide by 3. And so our y-intercept is equal to 5. If I asked for the coordinate, what would be the coordinate?
0, 5.
X is 0, y is 5. Okay, that would be the coordinate. If I asked the coordinate of the x-intercept, what would it be?
Negative 3, 0.
Negative 3 and 0, because x is negative 3, y is 0. With y-intercept, x is 0, y is 5. Okay, let's try a fun one. Even though this is not linear, let's look at a well, this is actually not even a quadratic. It's a circle. If you graph this, x squared plus y squared equals 16. So if I want the x-intercept, what will I do? Set y to 0. Set y to 0. Okay, so we have x squared plus 0 squared equals 16. Or what's x squared plus 0 squared? Sure, go ahead. Just x squared. If you're adding 0 to something, right? 2 plus 0 is still 2. X squared plus 0 still x squared equals 16. What do we have to do next? Square root. Now here's a thing that might be not very common to you. When you square root both sides, and this wasn't an issue before because when we had problems where we were square rooting both sides, it usually was in measurement. And we were solving for things like radius or a side when we had an area, okay? Now, can you have a negative dimension? Can you have a negative radius? Or no, right? A measurement in terms of like a negative radius or a negative side length? No, you can't. And so we didn't have to worry about the plus or minus. But here, is this a conceptual, a word, or not word, just give me a second. Is this a contextualized problem where it's like area or no, right? It's just an equation. When you square root both sides, there's actually two answers. There's the positive version and the negative version. It equals plus or minus 4. Why? Think about x squared equals 16. Why are there two answers to x squared equals 16? It can be a negative or a positive. If you square negative 4, is it equal to positive 16? Is negative 4 squared equal to positive 16? Make sure it's in brackets in your calculator. Grab your calculator. Yes. Why? Tell me why a negative times a negative is a positive. Remember when we square, it's the same thing as multiplying by the same thing twice. And a negative times a negative give a positive. So there's two solutions, plus or minus 4. Hence why we're going to have two x-intercepts. One of the solutions would be when 4 and 0, and the other one would be negative 4 and 0. There's two x-intercepts with this. Now you can't graph this on your calculator on this one because it's not a function. And your calculators can only graph functions. We can only graph things that are y equals. You can't isolate for y in this case. You'd have to make two separate equations to actually make this. Okay? So you would actually have to graph, if you were trying to graph this, which I know some of you were, you'd have to subtract, you isolate y, so I subtract x squared to the other side, and then we square root, but you'd have to do one for the plus, one for the minus. Okay? You'd have to do 1 plus root x 16 minus x squared and 1 minus square root, okay? So, not a function. So if you were trying to plug that in. Okay, so y-intercept. Set x to 0. So now we replace x with 0, which means we're left with y squared equals 16, and y would equal then, if we square root both sides, plus or minus 4. So we have two x-intercepts, or sorry, not x, y-intercepts. What are the coordinates? So who's 0 in a y-intercept? X. The x is 0. And then one's a positive 4 and one's a negative 4. Those would be your intercepts. Okay, we're doing really good. We have one more question and we're done today's lesson. Nice and short today. Okay? What? You finished your homework in class. Okay, so we're going to look at this guy. I'm going to have to zoom out. Because you need to be able to take a problem that has a context and tell me what the x and y y-intercept and x-intercept means in the context of that problem. So for example, I'm just going to add a page here. If I was dealing with throwing a ball, okay, in the air. I threw a ball. This is my height. I'm not going to tell you how tall I am. You can take a guess. But this is time here. Time versus height. Okay, I throw a ball in the air, and then it comes down. Okay? Now, in the context of this problem, the y-intercept, or the, I guess we can call it the h-intercept, mean? The height when? The height, so the initial height when you throw the ball. Because this is when time is equal to what? Time is equal to what at this point? Nope. Time. This is an axis. H-axis and a t-axis. At this very moment of time, it's at the very beginning. Full of potential. Okay, no potential, no kinetic. Time is zero. Okay? When time is, because it's the initial height. When time is zero, right? We usually say when the y-intercept is when x is zero. Well, what is our x? Our x is time. Okay, you have to be able to look at this problem and tell me what each represent. Now, tell me what the t-intercept represents.
The initial time?
Nope.
End of time?
End of time. I like how you wrote that. Okay, so it is the time. The time when what?
The ball drops.
The ball hits the ground. Ball hits the ground, right? Because your height is...
The time go down?
Oh, oops. The ball...
What are you thinking?
I don't know. Bound. I was thinking ball and ground. That's what I was thinking. The time the ball hits the ground, because it's when your height is zero. When's your height zero? That's at the ground. Right? So the time, because that's your x, when the ball hits the ground. So that's what we have to be able to do as well in this unit, is interpret graphs and what they mean. Okay? So looking at this problem, we are dealing with what two things? A lot of things. So let's read this twice. Lisa purchases a new car for $20,000. The value of the car can be represented by the formula V equals 20,000 minus 1250t, where V is the value of the car in dollars and T is the age of the car in years. Okay, let's go through that again. Lisa purchased a new car for $20,000. Okay, I see the 20,000 in the equation. So that's somehow related, right? The value of the car can be represented by the formula. Oh, okay, so that tells me what? Okay, that V is the value, because the value of the car is represented by. Okay, so V is value of the car. What is value of car? Price, right? Car in dollars. It's a price. And T is the time. The age of the car. So years, in specifically years. Now, the first thing they want me to do is complete the table of values and plot the ordered pairs. So they give me, why did they choose T as the input?
Because the amount of time it takes for the car to age.
Okay, so amount of time of the car, how old it is, will determine
How much it's worth.
how much it's worth. So your input is time. Your independent variable is always time, right? If you compare it to a y equals equation, right? Y is over here. The dependent variable is always here. This will be the independent. This is always your input. You input the T, and out comes the V, the value. You input your time, the output is the value. Okay, so we're going to put in time. We're inputting 0. Grab your calculators, everybody. So let's input into this equation time of 0. So 20,000 minus 1250 times our t value. What's my t value? What's my input? 0. Is that a shock to us?
No.
Why is that not a shock?
Because 1,000 minus 0 is 0.
Okay, so anything times 0, yeah. Where did we see that 20,000 before? How much you purchased the car at. And when you purchase the car, that's a time or year 0. That's the very beginning of time. I like that. So that makes sense to us. Okay, can we plot that on our graph? Right there. So we expected that. In fact, I didn't really even need to use the equation because I knew I bought the car for $20,000. That's the initial value. That's going to be when time is 0. Okay, let's put it in 2 now. So here's the thing. You can go second, enter on your calculator. And then all you got to do is change the 0 to a 2. Second, enter. 17,500. So we need to plot that. Okay, this is a big graph. So we're going up by ones on the, so that's good. 17,500 would be right here, year 2. Okay, because they're each worth 1 on the horizontal, right? Okay, 4. So go second, enter. Second, enter, and then I could just go back arrow, change the 2 to a 4. Isn't that a lot easier than retyping it every time? 15,000. Do you see a pattern? No? Poor girl. Don't buy a car. Well, cars are nice, but they're worst investment unless you buy like extreme luxury vehicles because they always depreciate. The moment you drive it off the lot, yep. So, yeah. But this is coming from somebody who doesn't love cars. Like, I'm not somebody who gets the whole like loving cars thing. So it's just like, why spend my money on something other than it has to be practical and not break down on me? Because it's just not a good investment. Yeah. Okay. So are you getting, double check that you're using a minus sign instead of a negative sign. That's most likely what it is. Because that happens often. Try it one more time. That was it. Okay, 6. What was 6 equal to? 12,000? 500. Every 2 years, we're going down by $2,500. So 6 was 12,500. Oops, let's close that. Getting in my way. Okay, did you plot yours? All right, we need to connect the line. If you'd like a ruler, you can grab one. Otherwise, you can use your calculator or a book. There's some here if you want a ruler. Okay. So what we want to do is draw that line. Go through all those points nicely. Okay. You want to perfectly go through all these points. Okay. Now, really quickly, does it make sense to connect these points?
No.
Okay. So, do the points in between make sense? So, can you figure out your value at 2.5 years?
Yeah.
Yeah. Right? Or does it make sense to have decimals? That's what I like to ask. Does it make sense to have decimals? We have decimals in terms of our value and in terms of how long you've owned it. Yeah, time and value. So it makes sense to actually connect these. Okay, this would be continuous data. There's a sharpener in the basket. I'm going to use that one. Okay, so let's talk about what 0-20,000 represents. Okay, so remember, what is my x variable here? What's the what was representing x? Instead of x, what did we use? Time, right? Down here. Or looking at our chart, our equation, the input. Time was our x, and what was our y? Value. So, what does that point represent again? We talked about it already. Yeah, Ishpa? Are you raising your hand? Oh, well, I should ask you anyways. Do you remember what this point represents? Initial value of the car. Right, when time is 0. Okay, let's estimate the t-intercept. Where does it approximately, Shiloh, put that away, please? Oh, okay. It just looks like you were texting. Sorry. So private with your calculator. What? Okay. The t-intercept. So where does it look like yours is crossing? I got 16. Yeah? I'll check your line. Especially if you use a ruler, it might be a little bit more accurate. Okay, so it looks like 16. 16 what? After 16 years, the value is? The value is 0. Now, is that realistic to real life? No, it's going to probably plateau. Actually, you know, it's not going to get, it might get to 0 when you have an accident right here. We write it off, right? Or you might drive, well, do many cars last 16 years nowadays? Yeah, they do, yeah. Yeah, it does depend, right? So it's a general trend, but not fully realistic of every situation. It's just like the trend of a value of a car. Okay, so use the graph to estimate the value of the car after 3 years. So after 3 years, I want to look, okay, 3 years is here. I'm going to go up. And that lands what value approximately? 16,000. Okay, 10 years. So again, go up at 10. See where it lands, ish. And then go across. $7,500. And then 14 years. 22,500. Okay, so they're saying use the formula to verify. Maybe we'll just do one of them. We verified the first one. They gave us when was v equal to 3 or t equal to 3. When t is equal to 3. And so I can plug that into my equation. V equals 20,000 minus, that's right, 1250 times 3. Plug that in. So you should be able to just go second enter again. Is that what we wrote? It was close enough. So we were a little off. We estimated, right? So what's more accurate? Yeah, the equation. Using the equation instead of using our graph, right? There's a time and place to estimate, and then there's a time not to. All right, use the graph to estimate when the car is worth 5,000. So now we're going to go to the 5,000 mark and go over. How many years approximately does that look like? 12 years? Okay, so we'll just do this one. Let's verify. This time they give us what? V or T? The value is 5,000. So we're going to plug that into our equation. 5,000 equals 20,000 minus 1250 t. I have to isolate what variable? Well, the only variable, T. So first step.
Full 50.
Mm,
Oh yeah, minus 20,000.
minus 20,000. Because there's no T over here. Which gives me 5,000 minus 20,000. Negative 15,000 equals, what's left over on this side? Positive or negative? Negative 1250t. And then we're going to divide both sides. Okay, plug that in your calculator. Tell me what it gives you. I'll go check after. That's why, could you imagine if there actually was another class there?
It'd be so quiet.
It'd be so noisy. They're going to put a brick, like a cemented wall in this June. Yay! This time it worked out. 12 years. I don't know. I'm going to go check after. Okay, the original value of the car is... It's all good. We're almost done. 20,000. It depreciates by how much per year? How much did it go down every year? No, that was it was 2,500. It went down 2,000 every 2 years. So how much did it depreciate every year? 12,050. Where else do you see 1,250? Right? Look at that. See that? Is that a coincidence? Rate of change? What? So it depreciates. It goes down by 1,250 per year and has no value after 16 years. Yay! Okay, the last thing I just need to talk about is a grade 9 term, and that's interpolation versus extrapolation. Do you remember that? You know the word. Okay, so in all of these, were we doing interpolation or extrapolation when we are estimating these values? Interpolation. Why is it interpolation? Inside. Interpolation is inside the given values, right? It's in between. Extrapolation is beyond. Beyond the diagram or the graph, beyond the given values. And so that's right here. It's not a very big concept in this unit. It's not probably something that you're really going to be tested too much on. It's just more of a review of terminology. Okay? So, if you can circle the following. You need to cover all of number 1. 2, A, B, C, and D. Okay, so no E and F. All of 1, yeah. All of 1 says, all you have to do is the y-intercept for 1, not both. And the second one's the x-intercept. Okay, 3, A, B, C, F. Kind of weird. So no D and E. A, B, C, and F. And no G, H, or I. And then 4 to 6, so number 4, 5, 6. And that's it. Is it? No 7. That's the last question. Yeah, and no 8 or 9. No. It's not too bad. But guess what? How much time you have? A lot. Okay? So let's get to work.